So I'll be the replacement speaker this time, introducing myself. I won't talk about data classification because I know too little about data classification, so I'll talk about a different topic I know little about, and it is quantum mechanics. I know slightly more about quantum mechanics than about data classification, but I'm not a physicist, so if you have a background in physics, I apologize. This will be a talk about quantum mechanics without any equations, which you might find really irritating. Anyway, so the basic topic of my talk is simply what is the world like if it is as quantum physics. I think for my purposes it doesn't really matter. So let's begin with this setup. What's happening here is there's a light emitter, sort of photon source, and there's a half-silvered mirror. A half-silvered mirror is just a mirror that lets through half of the light that comes in, nothing fancy. What happens if you put a detector over here, and if you repeat this experiment, is the detector goes click. Let's say it goes click when it detects a photon. The detector here will go click every other time, roughly. So 50% of the time when you do this, the detector goes click. And the other 50% of the time, if you put a detector here, that one will go click, which is not all that mysterious. You might think, well, what's happening is that the photon goes through half of the time and it gets reflected the other half of the time. Maybe because whether it goes through depends on exactly where it hits the mirror, you might think. Well, the electrons are sort of moving around. Maybe it sort of has to make its way through the electrons, and that determines whether it gets reflected or not. Or maybe it's some sort of indeterministic thing where really even if the electrons are at the exact same position, somehow the laws of physics don't tell us what happens. Sometimes it goes here, sometimes there, and there's no way to predict. In fact, neither of these is true. It's not even true at all that the photon either goes here or here. Here's what quantum physics actually says happens. What quantum physics says is that the photon passes through with an amplitude of, let's say, square root of a half, and it gets reflected with an amplitude of square root of a half times I, where I is the imaginary unit, the square root of -1. So that's what really happens. So if you ask what's the case at some later point, and then the truth of the matter is the photon is here with an amplitude of square root of a half, and it's over there with an amplitude of square root of a half times I, which is certainly more puzzling than one might have expected. According to quantum physics, physical states always have this weird amplitude. So even at the beginning, where we put the photon on its course, there was some amplitude of this configuration where the photon was heading towards the mirror. Let's say it was 1. Doesn't really matter. Let's say it was 1. And the laws of physics tell us how these amplitudes evolve. So the laws of physics tell us that if there's a photon heading towards the mirror and it starts with an amplitude 1, then it generates these two configurations, and the amplitudes of those two configurations are those two numbers. That's what the laws say, somewhat confusingly. So you see why there is the question somehow arises. We would like to understand what the world is like if that's true, because it's not even obvious what that's supposed to mean, right? What does it mean that the photon is here with an amplitude of square root of a half times I? What does that mean? So you can see that there is a question to be asked here. All right, so it's useful, since I have no equations, I will also get rid of numbers. So I'll just replace these complex numbers by arrows. If you think of a complex number as having a real dimension and an imaginary dimension, it's very natural to think of it as a number as pointing towards some point in the complex plane. So these are just representations of complex numbers. In this representation, it also becomes clear that a complex number carries kind of two sorts of information. The arrow has a length and it has a direction. And these sort of behave in different ways, and they have different features in quantum physics. And the laws of physics, the dynamical laws of physics, tell us how these arrows now behave. So they say if the photon goes towards a mirror, then these two future configurations are there. And let's say, this is not true, but let's just imagine that on the configuration where the photon goes through, the arrow remains in its previous direction, whereas on the reflected sort of configuration, the arrow is rotated 90 degrees to the left, so multiplied by I. is what the complex number here does. This is not too far from what quantum physics says. In fact, the photon goes in all kinds of other directions as well, so it's way more complicated and all this is continuous, but let's just imagine it's like this. So to see why, I should mention one more thing about these arrows. There is an important connection, according to quantum physics, between these arrows and probabilities of measurements. This is captured by the Bourne Rule. The Bourne Rule of quantum physics says that if you measure a system that's in some superposition of two configurations, then the probability of finding it at a particular position, you always find it in one. You never find a photon somehow being at two places at once. You find it here or there, and the probability of finding it here equals the square of the length of the arrow. The length of the arrow is also called the modulus of the complex number. So it's the squared modulus of the amplitude. So the complex number is the amplitude. The squared modulus of the amplitude of the configuration. That is the probability of finding it if you make a measurement. That is also very puzzling. I'll get back to that later. So that's a connection, a mysterious connection between these arrows and probabilities of measurements. Right, to see what all this arrow stuff and these weird superpositions is good for, let's look at this well-known setup. So I've added some more mirrors. These are normal mirrors that just reflect all the light that comes in, and this is another half-silvered mirror that lets half of the light through and half gets reflected. Well, as one would intuitively think. Okay, what happens if we set up things like this? Right, so if we try to apply the formalism of quantum physics, it's useful to go piece by piece. So before we saw that if the photon comes in here, there are these two future states that sort of are both created with different amplitudes, one where the photon is here and another where it's there. Let's just look what happens to the photon that's going along here, which has an arrow, as we previously saw, of pointing to the right. It gets reflected by this normal mirror, which we'll assume just does not change the arrow at all. And then it hits another half-silvered mirror, and here the same rule applies again that we had before. The mirror creates two of these new configurations, and on the one where the photon does not get reflected, passes through, the arrow remains the same, so it still points to the right. Whereas here, where the photon is reflected, we rotate the arrow 90 degrees to the left, so we get this arrow pointing up as the amplitude of the configuration here. It's just applying the formalism. You don't have to understand really why. I mean, I didn't really give you an explanation. Let's just say this is what quantum physics says would happen if there were only this starting point here. But there's, of course, also the other one. We also saw that there's a positive amplitude of the photon being here. And then we apply again the same rule. The one that passes through here, again, two future configurations arise, and the arrow does not rotate where it passes through, and where it gets reflected, we rotate to the left. All right, so we have, if you look at the outcome of these two branches, you'll see that we get the same configuration in the end from both. The same two configurations, either the photon is here or it's there, but they have very different amplitudes. Well, this one does. This one has the same on both of these. Right? It points up, but the other one points left or right. But a configuration, according to quantum physics, always has just one amplitude. There's always just one arrow. So what's the resulting arrow once we take into account of both of these? And the rule is simple, we add the arrows. Arrows are numbers, complex numbers, so you can add them. And adding arrows is kind of what you intuitively think you do. You sort of put the one at the end of the other, and that's the resulting arrow. So what happens if you add this arrow to that arrow is you get nothing, the number 0, because that's just exactly the inverse of the other. Whereas if you add this arrow together with this arrow, which points in the same direction with the same length, you just get a longer arrow in the same direction. So here's the outcome according to quantum physics. You get just one, you get this with sort of 0 amplitude, so we can ignore it, and you get this with an amplitude of, well, I here. So a long arrow pointing upwards. And remember the Bourne Rule? The Bourne Rule says if you measure where the photon is, you will find it at a certain place in proportion to the squared length of the arrow. So what is predicted is if you put a detector here and another here, and you set this up, you will always find the photon here, which is what you find. So if you set this up, that's what you find. And you'll see this is one indication of where this whole amplitude stuff and this idea that there are these different superpositions where the photon is both here and there does some work, because it's really hard to make sense of this outcome if you assume that the photon either goes here or there and it's somehow either indeterministic or depends on where exactly it hits. It's really hard to explain why then you would never find a photon up here. It would be even harder to explain what happens if we remove this mirror. If we remove this mirror, so that photon on that branch just travels along here, then of course there's no interference here. We can't add up another arrow pointing here in the other direction. So what will happen here is that's just the net outcome of removing that mirror. If you put detectors here and here and here, you find half of the time here, quarter of the time here, quarter of the time here, which is really puzzling. I mean, you're welcome to try, find some sort of analysis of what's going on here, assuming the photon is definitely always going one particular way. It's really hard, and there are more ways to nail nails into the coffin of this idea that there's just really one way the photon goes. But you're probably likely to give up already when you're trying to make sense of this. Okay, that was the basic picture. So we have two rules. We have Schrodinger's equation, which just tells you how these amplitudes flow. So there are all these, if you think of these configurations, as I've called them, a configuration roughly tells you where in a whole isolated physical system each of the bits of the system are. So this particle is here, and the electrons in the mirror are there, and so on. That's a configuration. And there's if you think of all possible configurations for a particular system, you get this very large configuration space. Since all these things are continuous, the photon could be at any point. There's an infinite space, and the Schrodinger's equation tells you how, given an amplitude at the beginning of some experiment, how it evolves through configuration space. So it says, initially, if it's initially concentrated on this configuration, then it will later be concentrated on those two different ones, where the photon is either here or there, and the amplitude here will be whatever it was, square root of 1/2 times I, and here it will be square root of 1/2, and so on. So Schrodinger's equation is one single equation which tells you how these amplitudes evolve and how these branches sort of evolve and merge again. And then we have the Bourne Rule, as I mentioned. The Bourne Rule, which says that when you measure the probability of finding a system in a certain configuration equals the squared modulus, the squared length of the arrow of the configuration. That's what quantum physics says. And what I want to know is, what does that all mean? So if you're a physicist and all you're interested in is predicting measurement outcomes, then that's all you want, right? Perfect. You have some sort of laws that you can always apply, and you get a rule for predicting, well, only probabilistically, but that's how things are. You get probabilistic predictions of measurements. And these predictions work really, really well. So nobody's ever found something where this doesn't work. So you make predictions, you set up various experiments, like with our mirrors, and you count the frequencies, and they always match the probabilities. How nice. So if all you want is some formal system, lots of equations, don't think about it, but it gives you the right results, perfect, you have all you want. As a philosopher, I'm not satisfied, because I think I would like physics to tell me what the world is really like, what the fundamental structure of the world is like, not only some machinery that allows me to predict measurement outcomes. I want to know, well, are there really these photons being at different places at the same time? What does that even mean? Is that really what the world is like? How do we make sense of this Bourne Rule? Is there a special rule for measurements somehow in the laws of nature? I want to know a little more than what this standard picture tells me. I'm not criticizing here physicists who don't care or have been trained to not care. A lot of physicists start caring and then are told to shut up and calculate and to no longer care. But at any rate, I care. I would like to know a little more of what reality looks like. So the first question that arises then, if we want to take seriously that what I just told you, what quantum physics says, just in all complicated equations, if that's what reality is like, the first thing we have to somehow come to terms with is the idea that really the photon can be somehow both here and here with an amplitude of square root of 1/2 and square root of 1/2 times I. We somehow just have to come to terms with that that's a correct description of fundamental reality. Here it might help a little to realize that quantum physics does not really care about the identity of particles. So people in the 60s, few people in the 60s thought that quantum physics violates classical logic, because it says that the particle is both here and here, but it's also not at the same place at the same time. Quantum physics says no particle can be at the same place at the same time. They're not universals that are somehow co-located at different places. So it looks like we have a contradiction here in fundamental physics. I think this is not a very charitable interpretation of what quantum physics says, because, as I said, quantum physics doesn't really say that this photon here is the same as that. Even if it did say that, it's questionable whether we would have a violation of classical logic. At any rate, it doesn't. Quantum physics makes no claims about particle identity. Really what it says is that there's an amplitude of square root of a half times I for a configuration where a photon is located here. And there's a square root of half amplitude to a configuration where a photon is here. And it's sort of natural to think that that's the same photon as the earlier one, but quantum physics just doesn't say anything on this. It's sort of agnostic on particle identity. Some people have claimed that actually assuming that there is such a thing as particle identity is inconsistent with quantum physics. Doesn't really matter for our purposes. At any rate, let's just take for granted, which I think helps a little bit in coming to terms with this, that we don't have to think of this as being the same photon as that. Let's just say there's a photon here and there's a photon there. And of course, they both have somehow as their causal origin this one photon originally here. But now, I think there is at least halfway intuitive way to picture what's going on here. We just have to accept that reality has, as it were, a different degree of separating states. So if you think of, it would be easy to understand that there's a photon here and there's a photon there, and not here, but at a different location in space. If you had one experiment here, another there, there would be no puzzle. Or at different locations in time, it would not be puzzling that you find here a photon only here and not here, and at another time only here and not there. And quantum physics says there's another way of where things can be true or false, where they're separated not in time, space, but in some other dimension. So reality has, as it were, further dimension, separation in configuration space, ultimately. So somehow both of these are real. It's true that there's a photon here, and it's true that there's a photon there, and you don't sort of see it at once because they're separated not in time, not in space, but in configuration space. There's just this further degree of dimension, as it were, to reality where things can be separated. And we also have to accept somewhat mysteriously that these dimensions, that these configurations have this weird quantity that's measured by a complex number. So photons have mass. Why can't these configurations have an amplitude? So I think this is, it's not a satisfying picture. It's not what we expect the world to be like, but I think one can say, okay, that's what the world might be like. We have this sort of branching structure. So this is superposition as branching. We had one photon at one place before. Now we have really sort of the whole experiment, the whole system has branched into two systems that are separated in configuration space where it's going up, it's being reflected on one branch and not reflected on another. So this is this popular idea of physics as presenting as this picture of a branching tree. All right, so that was the one thing we have to come to terms with. There would be other things we could talk about, but the main thing I want to talk about is how to make sense of this Bourne rule, which is also part of quantum physics. And it's also puzzling because, so the Schrödinger equation gives us a complete deterministic dynamics of how these amplitudes evolve. And so what does this rule add? I mean, where do the probabilities come in since we have a deterministic physical system? Well, why do we have probabilities of measurement? And in any case, what's special about measurements? It's just a bit puzzling. There is one answer people gave early on, which is to assume that what this rule really says is that the Schrödinger dynamics holds for all systems except when they're measured. So the idea is the Bourne rule states an exception to the Schrödinger equation. It says that when you measure, then it's no longer true that sort of things just evolve by the Schrödinger equation, but rather all these superpositions that you previously had somehow collapse, and you'll find the system only at one position. So you get what are known as collapse theories of quantum mechanics. So here we make more precise what the theories say. We have the Schrödinger dynamics for unobserved systems, for systems where you don't make any measurements. And we have a different dynamical rule for measurements. When a system is observed, its superposition state collapses into a single configuration, and the probability of the resulting configuration equals the squared length of the arrow that this configuration had before the collapse. Right, so now we see why that's a probability, because we have a really indeterministic dynamics now. So up until you measure, it's all sort of deterministic, and you get all these many branches with their amplitudes. But once a measurement comes in, all these branches disappear except for one, and you get, but which one you get is not determined. Rather, it's only a probabilistic matter, and you get the probability is determined by the amplitude. Okay, so that's a theory. It's a really implausible theory, as I hope you'll agree. I mean, how could physics have such a sort of separate law for measurements? What's special about measurements from a physical perspective? So I don't really know why anyone ever found this plausible, but this is known as the Copenhagen Interpretation. I suspect that it was never really seriously accepted by anyone, but physicists who sort of don't really care, physicists who like to shut up and calculate, sometimes said things like this, because that seems to answer the question what the world is like, but they didn't really care and didn't really take it seriously. At any rate, I find it hard to think that anyone could take this seriously. So people have proposed some alternatives to this particular cause of collapse. So I've assumed it's the measurement that causes the collapse. There's one famous alternative which says that it's not measurement that causes the collapse of these superpositions, but it's consciousness. Once a conscious observer comes along and looks at something, this sort of makes all the different branches disappear and you only get one particular state. Well, this is maybe mildly more plausible than the previous one, but only mildly so. It might be attractive if you're, I don't know, a faith healer or some convinced dualist who thinks that, yeah, there must be these interactions between consciousness, which is some entirely different thing from all the physical stuff, and the physical stuff, they must somehow interact, and now quantum physics tells us how. Right, so the only remotely somewhat plausible version of collapse theories is what's known as the Grw theory, which assumes that it's not only a probabilistic matter what configuration you get after a collapse, but also when collapse happens is a probabilistic matter. And the probability of a collapse to happen increases the more particles are involved in a system. So the more, if you have a sort of the single photon traveling along, it's almost certain the probability is very low for having any collapse at all, but it's not zero. And once you have the particles in a mirror involved, the probability gets higher. Once there's a measurement instrument or somebody like us, lots of particles, the probability is very high indeed. This is why once we have measurements, the probability of collapse is pretty much always 1. And so you always have collapsed systems when you measure, but there's no sort of weird special status assigned to measurements or consciousness. It's just that there are a lot of particles involved in these things. All right. All of these accounts have various theoretical problems. I mean, nobody ever worked out the measurement theory because it's so ridiculous. Consciousness, I know that Dave Chalmers, with a PhD student, once tried to spell it out and gave up because he couldn't make it to work. I mean, it's one thing to say, yeah, consciousness collapses, but you want to spell out the details and you just don't get any sensible results. This one has been worked out by far the most, and there's still all kinds of problems. I won't get into them. I'll just mention that these collapse theories have various problems that some people hope can be overcome. I want to talk about something else, namely, let's assume one of these collapse theories is correct. In fact, let's assume the silly measurement theory is correct, the Copenhagen theory. And then let's ask what the Bourne Rule means. So the Bourne Rule says we have this dynamical collapse. So we have when a system is observed, its superposition state collapses, and the probability of the resulting state equals the amplitude, the squared modulus of the amplitude of the configuration before the collapse. And I would like to know, what does that mean, the probability here? A very philosophical question, a question we can ask about probabilities everywhere in scientific theories. You find probabilities that look a bit like this in other scientific theories, in statistical mechanics, in stochastic chemical kinetics, in genetics. There are often these claims about probability, and at least as philosophers, I think also as a scientist, but at least as a philosopher, it's reasonable to wonder what exactly these claims mean. Especially if you consider that there are a lot of proposals that have been put forward that are pulling in very different directions. So the main proposals that still have defenders, there are others of mostly historical interest, are three. And so they're very different. The first says probability here means rational degree of belief. The second, so an epistemic theory of probability. The second says that they're fundamental propensities, they're sort of fundamental physical properties that sort of determine a state's propensity to evolve in one way or another, and it's not reducible to anything else. And the third possibility is that probability here means something Humean, something like frequency. So maybe the probability just is the relative frequency. So, and there are more sophisticated versions of this. Humean in this context just means that these probabilities are nothing over and above the actual sequence of outcomes. So if you look at all the outcomes of whatever relevant experiments we look at, then probability is interpreted as something that you can read off from these outcomes. Frequency is the obvious example that you can just read off by being given the entire sequence. Let's briefly go through these. Why do I go through these since we have such a ridiculous theory? In part because, as I said, the same question arises with much more reasonable theories in science, but also because I will later turn to a version of quantum mechanics, the Everett interpretation, which still talks about probability, even though it's not indeterministic, and I will try out the same possibilities then again. But let's try them out first here. All right, so epistemic version of our collapse theory. So remember, previously we had the Bourne Rule saying the probability, blah, 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 blah. And now I've replaced the probability with one's rational degree of belief. I mean, an obvious question if you talk about rational degrees of belief is who is the relevant agent? Whose rational degree of belief? Presumably not everyone's, right? I mean, somebody who has no idea of quantum physics, it would be sort of weird if their degree of belief matched the squared modulus of the pre-collapse configuration. So presumably what we mean here is that we're considering an agent who knows the rules of quantum physics, who knows the previous state of the system before it collapsed, but who does not yet know the post-collapse state, right? If you've already looked at, or if you've already heard, let's say, the detector go click, of course your degree of belief that the detector goes click is 1. It's not half. It doesn't equal the squared modulus of the pre-collapse amplitude. So we have to look at a very particular kind of agent, maybe there is none, but sort of a hypothetical agent who knows quantum physics, who knows the previous state, who doesn't know yet the post-collapse state. And for those, it at least seems that one could discuss that their rational degree of belief should match this amplitude. Okay, so that's one proposal. I won't say much about this, except that it seems extremely puzzling to me to think that a fundamental law of physics, and remember this is what we're dealing with here, we're assuming that there are these two different fundamental dynamical laws of how physical systems evolve. One for unobserved systems, one for measured systems, and the second law appeals to rational degrees of belief. The second law suddenly traffics in speculative normative psychology. Very weird that a fundamental physical theory should suddenly use psychological notions and give normative requirements. That just seems to me incredible. So I'll quickly move on to the next version, propensity theory. So here, again, I've replaced, so we had Bourne's rule, talks about probabilities, and now we assume that physical systems have this fundamental propensity. They have this graded disposition to evolve in one way or another, and this fundamental propensity just has a certain value. Since it's graded, it can be sort of more or less strongly graded towards one outcome than another. And so now our Bourne rule just says that this fundamental propensity to collapse into a given configuration equals this squared length of the arrow. Okay, that's the second proposal. There are actually two versions. Well, yeah, so we could ask whether this fundamental propensity, which propensity theorists think there is a further fundamental property. It's supposed to be some sort of primitive fundamental physical property. Propensity theorists say it's kind of like mass. So we could say, is propensity here something else over and above amplitude? We already have the amplitude, and we could interpret this red statement as an equation between the fundamental propensity, this further fundamental physical quantity, and the squared modulus of the amplitude. That's one version. We could do it. We could also say this is not actually an equation between two fundamental properties, but rather it's stating an identity of properties. It says that what the propensity is really the squared modulus. So it's not a further property, but it's an aspect of this property. It's the length, as it were. I mean, the squared length, but you can see that. So we wanted a fundamental physical property that reflects the dispositions to evolve in one way or another. And it seems that on this theory, we already have one. It's the length of the arrow. Why postulate another one and say the two are equal? All right, you could postulate a third one. So it seems to be the more economical version of this propensity view. It says that the system's propensity really just is the length of the arrow. It doesn't equal it, it is. So it's the same property, not just the same property value. So the red thing is not really a further law of nature, but just states an equality of properties. Either way, a well-known problem arises that would arise no matter what we say. But I think it's very easy to see if we make this move. And the problem is that the point of postulating Bourne's rule is to connect this whole formalism of quantum mechanics with empirical tests. So we don't see things in superposition. We see frequencies of outcome in repeated experiments. And Bourne's rule is supposed to tell us how we can read off what the amplitudes were, given that we get such and such frequencies. And to make that work, you need a connection between either frequencies and these amplitudes, or degrees of belief and the amplitudes. That's why the epistemic theory got that bit at least right, because it just said these probabilities are degrees of belief. So there is, of course, the connection between squared modulus and degrees of belief, even though it didn't explain us why that holds. So, but this account makes this very mysterious, because now the claim is that this holds, this third principle. When a system is observed, one's rational degree of belief in a given configuration equals the squared modulus of the pre-collapse amplitude. That's something, the pre-collapse amplitude, remember the squared modulus of this, that is the propensity. We have found what we wanted, a fundamental physical quantity that grounds the evolution. And now, of course, for this to do the work it's supposed to do, we need this connection. So we need this principle to be true. But why should this principle be true? Why should one's rational degree of belief equal the squared modulus of the pre-collapse amplitude? It could be a further physical law. Then we're just back at the epistemic theory, which postulated something much like this as a further physical law. And I complained, how could that be a physical law? It talks about rational degree of belief. If it's not a physical law, what is it? Is it some sort of norm of rationality? Some basic a priori norm of rationality? It certainly doesn't look like one. So, well-known objection, I'm convinced by it, that these propensity theories don't work. Even if we grant them that there is what they say there is, this fundamental physical quantity that represents propensities of evolving one way or another. So the last man standing are Humean theories. So here we replace the probability claim by, in the simplest version, a claim about relative frequency. So the Bourne rule would say that when a system is observed, there's a collapse, and among all experiments of the same type, the relative frequency of any resulting configuration equals this squared length of the arrow. Okay, this version of the Humean account obviously doesn't work for also well-known reasons, because, one reason is that many systems of which quantum physics talks are instantiated very rarely. Maybe only once, maybe 0 times, but they still have well-defined, the Bourne rule still gives you well-defined probabilities, which certainly don't equal the actual relative frequency, which is all 1, 0, or undefined if you run these experiments. There is a better version of Humean theories, and this is a version of the best system account. For those of you who don't know the theory, this will be a little bit quick. Much of what I say could be said in terms of frequencies. So I like this theory. If you find this a bit confusing, just the frequency theory and ignore the problems it has. So here's a theory that doesn't have the problems of frequentism. So the best systems account says that what it means. So first of all, we're back to the original statement with probabilities. We don't actually replace this by anything else. But what we say is that this at the moment does not yet have any interpretation. Rather, the empirical claim of quantum physics, when it puts forward those two laws, well, this silly Copenhagen quantum physics, when it puts forward those two laws, is that these laws provide the best systematization of all the actual events in the world. So if you think of all the outcomes of all possible experiments and all other observations people ever made, and you try to systematize this, you could just state it all explicitly, state everything explicitly. That would be a very long and very gerrymandered list. If you try to compress it, you'll find that it becomes very useful to have probabilities on the assumption that a probabilistic theory counts as a good systematization of actual events to the extent that its probabilities match the frequencies. So they don't have to match precisely, but it's better the more they fit. So this is roughly the idea. So the claim of quantum physics is not that this is true, because we don't actually have an interpretation of probability, but it's that this is the best systematization of all the occurrent events in the world. It strikes the best compromise, as Lewis said, between simplicity, strength, and probabilistic fit among all possible theories. So probabilistic fit is this, how close are the postulated probabilities to the actual frequencies. All right. I like this best out of a bad lot, one might say. The other ones were really bad. This is at least not quite as bad. Oh yeah, there's one thing that's nice about this, that if that's the interpretation of what quantum physics says, you can show that on quite mild and plausible independent assumptions about rationality, that your rational degrees of belief should be aligned with the probabilities that are postulated by a theory, which is crucial for testing. This is a controversial claim. I've written a paper, which you're welcome to read, arguing for this claim. Okay, let me move on now to the theory I more want to concentrate on. This is the Everett Theory. So the motivation for postulating collapse is a bit obscure. The main motivation seems to be that allegedly we never observe things in superpositions. That's what physicists said in those days, 50s and 60s. They said that if a system is in a superposition and we measure, then we always find it either here or there. So it can't be true that it's in this superposition once we measure. Otherwise, we would find it in a superposition. It's a bad argument because nobody ever explained what it would be like to find the system in a superposition. What's that supposed to be like so that we can tell this is not what we found? I mean, are we imagining that we would somehow, well, does the detector make click but not as loud as it would? Nobody ever gave any explanation of what the problem here is supposed to be. And what Everett, and before him actually Schrödinger, pointed out is that really the simple Schrödinger dynamics with this sort of branching interpretation doesn't contradict anything we ever experience, because human beings, observers, and other measurement instruments are just physical systems. They're part of physical reality. So if you can just apply this whole physical machinery, it becomes impossible to calculate, but in principle you can apply the machinery to physical observers who are standing there and listening to a detector. And what you get is, unsurprisingly, a superposition of the observer hearing the detector make click here, and the observer hearing a click here and not hearing it here. So you get a superposition of, let's say there's only a detector here, then it's easier. Then you get a superposition where on this branch, the observer hears a click, and on this branch, she doesn't. That's all you get. And if you think about this branching picture of what quantum physics says, then, well, if we ran the experiment and we, let's say, heard the detector go click, well, maybe we're just the person here. Right? I mean, on this picture, there is a person here who hears the detector go click. There's no weird sort of prediction that one would hear it click in some faint way or hear it click and not click. No, there's a prediction that there's a person here who hears the detector go click. And, well, if that's what we find, there's no contradiction between this basic picture without any collapse and our experience. So let's just get rid of this weird collapse postulate. So this is no collapse accounts. We have the package we had originally. So we have Schrödinger dynamics, no exceptions. Observations, measurements, no exceptions. We still have the Bourne Rule, which now is again rather puzzling. The Bourne Rule says in measurements, the probability of finding a system, what does that now mean? We have no collapse, we have no indeterminacy. This is a deterministic system, but somehow in measurements there are probabilities of finding outcomes. So what does this mean? what does probability mean? Right? Which in effect means, what does this statement mean? And we can try out, again, our three proposals. Epistemic version. This is what, to my knowledge, every single Everettian endorses in the world. So the idea is probability in the Bourne Rule really means rational degree of belief. So the rule says, in measurements, one's rational degree of belief in finding a system at a certain configuration equals the squared length of the arrow. Before I said, that's bizarre, how could that be a law of nature? But notice that for the Everettian, the Bourne Rule doesn't have to be a law of nature. In fact, the Everettian is quite insistent that the Schrödinger equation is the only dynamical law of nature. So this is the law of nature. This is something else. This is not a law of nature. This is something that has to be shown to be true based on sort of the basic picture of reality that quantum physics paints, together with independent principles of rationality. And here's a long list of authors who have tried to make exactly that argument, that they're independent principles of rationality, which together with the assumption of this branching structure that Everettian quantum mechanics tells us exists, that it then follows that the Bourne Rule is true. So, long list of people. We could try, well, I might briefly comment. For a long time, I was very skeptical of these proposals, of these attempts to derive the Bourne Rule from independent principles of rationality. I'm no longer as skeptical as I used to be. I'm now agnostic. I'm neither convinced that they work nor that they don't work. We could try the propensity account, but that I have no idea how that would work. So, because we have a deterministic system, and we somehow have to say in measurements, there are these fundamental propensities to evolve one way or another. I just have no idea how propensity theory could be applied to the Everettian account of quantum mechanics. But the Humean theories can, and this is something nobody ever tried out, and the point of my talk is let's try this out. As I said, all Everettians endorse the epistemic theory, but I think the Humean theory is by far the best, well, not this one, but the best system type account is by far the best theory of probabilities everywhere else in science, in statistical mechanics, in genetics, and so on. So why not at least give it a try when we deal with these probabilities in Everettian quantum physics? All right, so the simplest version, again, the frequency theory, would say that when you do measurement, the relative frequency of finding a system in a certain configuration equals squared one. Now, at least you can see that that's a coherent combination of statements. Here you have a dynamical law which describes this branching evolution of physical systems, and then you get a further statement telling you something about the relative frequencies of outcomes in this whole branching structure. The problem is that the further statement is false. So, because the relative frequency will not match in this whole branching universe, it just won't match the squared modulus of the amplitude. Let's try the somewhat better best systems type account. So here we would say we leave probability in there. So in measurements, the probability is so-and-so, just the original Bourne Rule. But we now say the empirical claim is that these two principles provide the best systematizations of all occurrent events in the world. It's false for the same reason that if you look at the whole branching structure, it's just not true that it's best systematized by an account that postulates these probabilities. In fact, it seems much better summarized by just the Schrödinger dynamics alone, which tells you all the branches, everything that happens. Why do you also need to say, and this is more likely than that? That just seems to add no information. Certainly doesn't make it give it any better fit or any more simplicity. So that's also false. Maybe this is the reason why nobody has really tried the Humean accounts. Well, if it were true, we would have this important problem solved, that we can explain what these Everettians try to do with their epistemic accounts. It would explain why the Bourne Rule is actually useful in testing. It's not true, so we're not there yet. Okay, but I think we can tweak the application of the Humean account. The tweak, to motivate the tweak, imagine something else. Imagine, as some cosmologists think, that the universe does not only comprise what we think of the universe, but there are also these other pockets of the universe where there are different worlds, as it were, with different laws. So there is not just our world with our laws, but there's also equally real other worlds with other laws. And there's this big pluriverse where we're only sort of a local pocket in. And if that's true, then one would think that we should be especially interested not just in laws that hold overall, of which there might be very few, but also in local laws, in what's true in our local sort of pocket of this big universe. And the same is true even if these cosmological models are false. Imagine that our universe, which is already quite large, has somewhat different laws, or well, let's say there are different regularities in our galaxy than in some very far away galaxy where whatever, it's close to a black hole and things behave very differently. And it seems like it would be quite interesting to know regularities that obtain not in the whole universe, but in our galaxy, where things are particular ways. So it seems to make sense that we want these kind of systems that systematize not only overall truths in the world, but also local truths in our region of the world. And now we can fix the problem. So we try, again, we go straight to the best systems type account. So now the idea roughly is that the probabilities you find in Everettian quantum physics together with the Schrödinger dynamics give you the best systematization, not of the whole branching structure, but of our branch. We're just on one of these branches. We're not everywhere. We're on one of those branches. And the probabilities in Everettian quantum mechanics, they have close probabilistic fit with our branch. Not with the whole thing, but with our branch. And if you think about it, if you want to predict what happens on our branch, you have to use probabilities. There's no sort of deterministic way of predicting what happens, let's say, in the past of our branch. Probabilities are really, really useful in systematizing what goes on here. So that's the basic idea I want to put forward. Seems like something one could try out. As I said, if that works, then we immediately get what is often considered the main problem of Everettian quantum mechanics to explain this connection between Everettian probabilities and rational degree of belief by the general theorem that these best system probabilities are aligned with rational degree of belief. So I think it's worth trying because it seems, at least on the surface, to work. There's one question before I close. Well, I'll have one more other thing. But so this is a question that I think is a little troubling on that picture. So I've assumed that quantum physics paints a correct picture of fundamental reality when it says there are these branching superpositions and they have these fundamental properties, these amplitudes. And now on the proposal I've made, it somehow turns out that on our branch, if you systematize the outcomes that happen on our branch, it's useful to use probabilities that exactly coincide with the square of the length of these fundamental properties. It's a little strange. Is that a coincidence? Is it if you were in another branch, would you have a best system where the probabilities just don't align with these amplitudes at all? Because the amplitudes are built into the fundamental physical structure. They don't vary from branch to branch. They're just baked into reality. And somehow on our branch, surely there are many branches where the outcomes are not best systematized by probabilities that match those amplitudes. There are outcomes where you always follow the unlikely outcome, and then that's not best systematized by these. So it seems like it's kind of weird that we happen to live on a branch where the amplitudes and match the probabilities in the best system. All right, answer. There are these symmetry arguments that I mentioned about which I'm agnostic, and they seem to suggest that there are actually a priori reasons to suspect that our branch is one where the probabilities, so let's say the frequencies, closely match the squared amplitudes, which is surprising. This is sort of the reason why I always was skeptical. How could there be an a priori reason to think that? But I more and more think maybe there's some truth to that. And the reason is that there's the amplitudes are not nearly as arbitrary as one might think, or as I, as a non-physicist, always thought they are. It's sort of a comparison just to get the idea across. Consider a world that consists of smaller pockets, and each pocket is a sequence of 1,000 coin tosses. And you have all the possible sequences. Each of them is one of these little worlds. So there's one world where there's 1,000 heads, one with 1,000 tails, but many, 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 many more worlds where you have roughly equally many heads and tails. Almost all these worlds, of which there are many, have roughly equally many heads and tails. Moreover, almost all of them have the heads and tails in a very disorderly fashion. There are very few regular ways compared to the irregular ways. And so if you think of the branches, if there's something like this, if there's something like all these possible outcomes of 1,000 coin tosses, then you can see why it could be on independent grounds of rationality that if all you knew that you were in one of those worlds, then it would be rational to assume that the relative frequency in our little world is roughly half, and that is a very disorderly sequence. In other words, that it's best systematized by saying this is a Bernoulli sequence with probability half. So this is sort of the idea that we can say something similar about the Everettian branching structure, that it's actually not some sort of, it's not totally random that our branch displays these patterns, because loosely speaking, almost all branches do, and it would be very odd, in fact, to be on one of those others. Okay, fallback position, another Humean interpretation. This is, I think, the last slide, second to last. Suppose the amplitudes are arbitrary in a way where I'm not sure if they are because I'm not physicist enough. Then there's another thing we could try. I've assumed, as I said, that the amplitudes are sort of baked into fundamental reality. We could say they're not. We could say that they're more like the best system probabilities, which don't represent some aspect of fundamental reality, but just a statistical summary of actual outcomes. So that would mean fundamental reality looks like this. There's this branching structure, but there are no objective arrows in it. And rather, the arrows we postulate because that gives us a nice systematization of our branch. So this is another approach. Since we're out of time, I'll leave discussion of this to question time. I'm done. Thank you very much.